as another application of the rule we just used, let's solve the equation 7 to the 3x equals 12. Now there are lots of ways to use logarithms to do this, but let's just exercise what we know about log to the base 7, or logs to bases. Log to the base 7 of 7 to the 3x then should equal log to the base 7 of 12. Now we use log to the base 7 of 7 to the 3x because of the property that says the log to base 5 of 5 to the x equals x. Whatever we take log to the base 5 of 5 to the x, whatever the x is, that's what we're going to get here. Well, same thing applies to log to the base 7 or any other base. Log to the base 7 of 7 to a power is just the power. Because these are inverse functions, we just end up with 3x here. So 3x is log to the base 7 of 12. So we can easily calculate log to the base 7 of 12. That's log 12 over log 7. And that's approximately, if I'm to believe the people that told me, it's 1.28. Then if we solve this for x, we're going to divide both sides by 3. We're going to get x approximately 1.28 divided by 3, 0.426 bar. That's probably too many significant figures, maybe rounded off to 0.43 or 0.427. But anyhow, this is how we could solve this equation very easily. So when we see a variable in an exponent, whatever that base is, we take log to that base of both sides, and we're going to end up with the variable coming out of the exponent, and then we can solve it. In most cases, provided the laws of logarithms aren't violated. There are places where we can't do this, as we'll see. Let's apply what we've just found out about logs to the doubling time of the situation where we had $10,000 invested at 7% interest. Remember that the y was then $10,000 times 1.07 to the t, and that the doubling time is the time that satisfies this relationship here. The $10,000 times 1.07 to the t plus t dub equals 2 times $10,000 times 1.07 to the t. And if you don't remember the details of that, refer to the notes from the last class where we went through this idea in detail. But the basic idea is if you go to time t dub later than t, which is t plus t dub, you're going to end up with twice as much money. Because that's what the doubling time is. It's the time it takes to double your money. Now solving this, again, by means that we used earlier, we'll divide both sides by $10,000, and we'll use the laws of exponents here, and it's going to turn out that we have 1.07 to the t dub equals 2. We got down to this point. How do we solve from there? Well, let's just take the log to the base 1.07 of 1.07 to the t dub. And of course log base 1.07 of this side, because we got to take the log base 107 of this side if we're going to do it on this side in order to maintain the equality. Looking a little more closely at the solution. Log to the 1.07 of 1.07 to the t dub by the inverse function here just gives us t dub. Log to the base 2 of log to the base 1.07 of 2 is just what? That's log of 2 divided by log of 1.07, which is about 10.2. Now you did this problem for homework, I believe, or we did it in class, and we did find a doubling time of about 10.2 years. Of course, in this case, we can go to as many decimals as we like, or as many as your calculator gives us, and find the doubling time as precisely as we wish. We could find the doubling time down to the second using the calculator very easily.